Hello, everyone. I'm checking out some stuff while I'm waiting for everybody to log in. If anybody has any questions, go ahead and feel free to ask me right now. I should be able to spare enough CPU time in my brain to answer the questions while searching for something as well.
Um, have you decided when the final was going to be?
Yes, so the final is definitely going to be the week of. Well, you'll be able to take the final exam period starts basically kind of weirdly on a Tuesday. So the final exam period is from Monday. I want to say the date is the 3rd until Monday the 10th. So what I'll have available for you guys is you'll be able to take it on Wednesday, which should be that what 4th, 5th. I think that's the 5th. Let me double check my calendar. But if need be, someone may be able to take it. I might be able to set it up for you to take it as early as the 3rd if someone needs to get out of town quick or something like that. So your choices really will be the 5th, or then you'd have to actually take it on the following week, which would be the last day of classes. But I prefer not to do that. And of course, that date would be the 10th. So I'm shooting for the exam date to be due by the 5th.
Okay.
And if y'all can respond to us, if you can't do that, then you got to make sure you make your own appointment with the testing center and all that good stuff.
Thank you.
Okay, no problem. Anybody have any other questions? Okay, so you do have a test that's due supposedly tonight at 11:59 p.m. Anybody have any difficulties getting that done for sure? I could possibly give you one more day, but that's it.
I think it was already due. When I checked, it said like 5:04 p.m. or something.
Well, that's weird. Okay. Yeah, I thought I made it to midnight. Yeah, you're right. It was actually due at 5:45. Did anyone miss it? Let's put it that way, because I'm willing to open it up until 11:59 tomorrow evening, just in case. I'd rather not give a bunch of zeros right now. That's going to hurt a lot of grades. So everybody here, y'all made the test. Y'all got it done. Got as many attempts as you wanted, that sort of thing. All right, we'll leave it be then. What I'm going to do is the next test, I should be able to open it up Wednesday or Thursday of this week, and it'll be due basically by Monday at 5:45 p.m. So I'll try to open it up as early as possible, but I think we should be in a good spot to do that. So anyone have any other questions? Looks like, I guess, as many people that are coming are here now. No questiones? All right, well, let's go ahead and get started. We were in chapter 18, and I essentially finished chapter 18, but I wanted to work a couple of examples. So I actually specifically told you to do some examples from the book yourself, and that's fine. It's just I'd like to sort of talk to you a little bit about how some of this stuff was done, some simple problems as well. And I'm going to actually jump into chapter 19 as well. That's why I have the order kind of weird in these problem sets that you'll see. Really, the first thing I'm going to do is the last question. I'm not going to do anything on diffusion, but I am doing stuff on mean free path, and I'd like to talk to you about that. So let me start off with the idea of what mean free path is, and then we'll use that to solve a problem. Okay, so I'm going to turn on my document cam, and if you think about the path that an actual molecule will go through, so you can look at a molecule and pretend it's roughly a sphere. That sphere has a radius r, say. Now, if its center comes within 2r from another center of another molecule that's identical, then they'll actually collide. So what we do is we imagine this thing going off in a straight line this way, and we imagine a little cylindrical tube that it's going through, when in actuality, there's no such tube. It's just sort of that's the area upon which, if the centers of any other molecules are in there, then it will collide. So what you do is you assume this thing is traveling in this direction. And it's an arbitrary direction, even though I've drawn it to the right. I'm just choosing any random direction and I'm representing it as to the right. And let's say it has an average velocity v bar. Okay, you might argue that that should be the root mean square. You might argue that that should be the mean velocity, like we calculated in an example, I think 18.5. Or you might even say it's something else, the most probable speed, all sorts of stuff. But the main thing is we're going to treat it as if it's some average velocity. Well, if that's the case, then the distance that it will travel in a time delta t would be that average velocity times delta t. And that should be basically the volume through which it has to actually travel. And if any other molecules have their center inside of there, ignoring right now for them to actually be moving, if any of them have their centered inside of it, then there is definitely going to be a collision. So what we might calculate is try to figure out basically how big this volume is. And when we figure out how big this volume is, we can figure out how many molecules there are. And then when we get the number of molecules whose centers are actually in there, then that'll be the number of molecules that would cause a collision in a time delta t, assuming the thing was going at a velocity v, v bar, I should say. So if we try to do that, then we can say, all right, well, the number of collisions that occur in a time delta t should be equal to the volume of this times the density of it. Well, the density of it would be the number of molecules or atoms, if you're talking about pure element, divided by the volume. So that's the number density of molecules or atoms. So this is literally the number of molecules you'd have in a given volume. And now if you multiply that, of course, times the volume of this actual shape, which is, of course, pi, times the radius of the shape. Now, what we have to do, since we want it to be such that any molecule center in there means it's going to collide, then we have to say this r here is actually equal to twice the radius of the molecule. So we'll say pi times 2r squared is the cross-sectional area. Now, if we multiply that by the length, which is v delta t, then we actually have the volume. So now what we have here is basically the volume density of, or excuse me, the number density of molecules times the volume of the sample of mass that we're doing. And that, of course, gives us a number of collisions in the time delta t. So this equals the number of collisions if we can deal with that thing about the fact that the actual molecules are moving, so it's not really fair to say that. Well, it turns out if you actually do a good analysis of this, then what you want is not the velocity of this, you want the relative velocity of it compared to every other molecule. Then you're taking into account the fact that all the other molecules are actually working, or excuse me, actually moving. And to do that, you basically let v go to the square root of 2 times v bar. Okay, so when you get that, then you know that the actual answer is n over v times 4 pi r squared v bar delta t equals a number of collisions in a time delta t. Okay. Now, if you take the reciprocal of this quantity right here, 1 divided by it, then what you'll get instead of the number of collisions per time, you'll get the amount of time that happens between collisions. Okay, and this isn't really collisions per time. I should just say this is number of collisions total. So when you flip this over, this will actually give you the mean free path. All you have to do is take this, flip it over, and then multiply it by the actual distance that it'll travel, and that'll give you, that'll take into account the fact that you're actually doing this per unit time dt. So that means the mean path, L sub m is what your book's calling. I think they use the lowercase. No, they use uppercase m. So if you flip this over and multiply it by v delta t, so this is actually going to be square, or actually v delta t, like this. That's the distance it's going to travel. And then, of course, you are taking, I don't know why I wrote an N down here. That's supposed to be another V like it was up there. Now you have to take into account the fact that the relative velocity is going on, is what's important down here at the bottom. So it'll be 4 pi r squared times the square root of 2, which for some reason I didn't write in there, which is the whole reason I rewrote that, was to put that square root of 2 in there. So note, square root of 2. Okay. So square root of 2 times v bar times delta t. Now I can get rid of this thing that just looks stupid, that I made a mistake on there. I could actually do that with that, but I think it would be making more of a mess. So I'm going to leave it be. So now I've got that the mean free path really is independent of the velocity, because I took the distance it's traveled, multiplied that by the, divided that by the number of collisions per time, and that actually gives me the number, the length of travel for which the atom or molecule travels before making a collision. So you can see the V delta T drops out, and I end up getting basically one. Oh, where'd my N over V go? I left that off too. Jesus. N over V, sorry. So putting that N over V back in there, now I get that the mean free path is in fact equal to 4 pi r squared square root 2, and then that's times N over V, and all that's in the denominator. Okay, so that is really the mean free path, and it should come out in meters. If you look at the actual units, it is going to come out in meters. This is, for instance, number per cubic meter. That's a square meter. So you're going to see basically a cubic meter, a square meter divided by a cubic meter, which means a meter in the denominator, but that's already in the denominator, so that becomes a meter on top, and that's exactly it. So this is the formula you should use. It's one of the formulas I would recommend, and actually, that one too, that I would actually recommend you having on your equation sheet. Now that we have some understanding of how that works out, you'll see there's some other problems where they sort of walk you through that in your homework. But I would like to have you work a problem right now. I'm just going to change the number of it. It's currently listed as number 3. So let me share my screen with this problem, I believe, or this page. Yes. Okay. So what I am going to do, see if I actually, oh yeah, I did do something that was, okay, so what I want to do is I'm going to put this at the very last. So I'm going to call this problem 4, but when I erase it, it's going to become back number 3 or something. I'm going to put this as number 1. And then I'll do okay, I lost one of my problems. Oh, there it is. Whew, scared me. Okay, so that's problem number 1 is about the average number of collisions. Number 2 is basically a relative humidity question. And then this number 3 I've already asked as number 1, so that'll be number 3 there. So that's really the problems we're working on. Let me save that real quick. So the first problem is, what is the average number of collisions of air molecules in a time of 1.00 milliseconds if the temperature is 20 degrees Celsius and the pressure is 1.01 times 10 to the 5th Pascal? And part B, what is the mean free path of air molecules? Note the diameter of the O2 and N2 are roughly the same, 3 times 10 to the negative 10th meters. So I'm looking at problem 1 now. What I have is that delta T is equal to 1.0 times 10 to the, I'm going to show you this in a second, 1 times 10 to the negative 3 seconds. I've got the temperature, which is capital T, is 20 degrees Celsius. I've got that it's basically air which is approximately 80% N2 and 20% O2. And we have the pressure P is equal to 1.01 times 10 to the 5th Pascal. And I'm going to say D, the diameter, is equal to 3.00 times 10 to the negative 10th meters. Probably I should only use 1 0 there because in reality, I'm just estimating that based on 2 sig figs, not 3. So let me kill that other 0 there. All right, so that's my data, right? So let's stop sharing the screen a second. And first, what I want to know is how many collisions. So A is number of collisions in delta T. And part B is what is the mean free path? So they literally just wanted to know L sub M. Okay, so now I can kill this because I've got all the information from the problem that I needed. I'm going to stop sharing. And now looking at this problem, we can go about solving it. What we found earlier was that the number of collisions in the time delta T really should have been basically N over V. That's again the number density times 4 pi r squared times the square root of 2 times V times delta T, and that's V bar, okay? So again, this square root of 2 takes into account the relative velocity issue, or actually the fact that the other molecules are moving because we're using relative velocity relative to the other molecules as opposed to just the average velocity without taking into account the other things. So when I do this, all I have to do is I got to figure out what N over V is. Well, we know for an ideal gas that a mole of a substance has a very specific volume. This is one of those things that I said, you know, every physics and chemistry and maybe even every biology major should know this off the top of their head, specifically that a mole at standard temperature and pressure really should be about 22.4 liters. Now, if you change that temperature instead of 0 degrees Celsius, which is what standard temperature and pressure is, the temperature will go up to 293 Kelvin instead of 273, but that's not a huge difference. That being said, we should probably, just to be careful, go ahead and estimate it. But this was an estimate problem when your book did one like this. So you can say, I suspect since the temperature is going to be 273, the volume, or since the temperature at 273 gave a volume of 22.4 liters, I suspect bumping it up by 20 degrees Celsius to 293 Kelvin would maybe make it a little bit bigger volume. And you might even try to estimate the volume to be 22.9 or 23.2 or something like that. Or you could just use the ideal gas law and calculate it again. But since I'm doing an estimate, I'm just going to do N over V as if it's 0 degrees Celsius and not worry too much about it. So N over V, since it's a mole, we know that 6.022 times 10 to the 23rd molecules per mole. But we also know, I'm estimating, of course, that a volume of a single mole takes up a volume of 22.4 liters. And of course, a liter is 10 to the negative third cubic meter. So it's 22.4 times 10 to the negative third, left off the 10 there, cubic meters. So you can see what's going to happen here is I'll get molecules per cubic meter. And the fact that you're using a mole doesn't really matter. So you can erase that at will. And when I do this calculation, I get 2.69, I think 2.69 times 10 to the 25th. Yes. This comes out to 2.69 times 10 to the 25th molecules per cubic meter. Okay. Y'all should verify that, of course, with your own calculation. But now I've got N over V. Now, what about V? Well, V, what I'm going to use? Well, we happen to know, for instance, that the root mean square velocity can be given from our Boltzmann distribution. Remember when we did the derivation of the ideal gas law, and then we converted it in terms of not in lowercase n the number of moles, but in terms of the big N, the total number of particles. What we found then was the root mean square velocity was easy to determine, specifically that the average kinetic energy is equal to 1/2 mv squared average, say, and that actually turns out to be 3/2 kt. So if I actually wanted the velocity, I could say, well, the velocity is equal to the square root of 3 kt over m. And this was actually what we termed the root mean square velocity, not quote unquote the mean velocity, but it's in the ballpark. And again, we're just asked to estimate this. So I'm going to go with that. So here's the problem. You get a different velocity whether you're using the mass m for the N2 or the mass m for the O2. And what we're talking about is molecules in general. So what I'm going to do is I'm going to say the mass for air is about equal to, and in this case, we're going to say 0.80 times the mass of nitrogen, because nitrogen is about 80% of the atmosphere, and that's roughly 4.6 times 10 to the negative 26. Kilograms. And then we could say plus 0.20, again, this is approximation, times the mass of the actual, excuse me, I got that one. No, I did get it right. Okay. Times the mass of the oxygen, which is 5.3, times 10 to the negative 26 kilograms. That actually works, and I could plug it in here and get a value. Or how about this? I could also use the velocity for the nitrogen, which happened to be done in example 18.2 in your book, where we found VRMS for N2, and this is at room temperature, was actually equal to, since the nitrogen is a little bit lighter, it actually had a little bit larger speed, so that's 510 meters per second. And we also found that VRMS for O2, again at 20 degrees Celsius, in that case came up to about 480 meters per second. So with that, you could also do the same process and just take 80% of the 510 and add to it 20% of the 480. When you do that, you get roughly an average velocity of all the molecules equal to about 500 and I think I got 503 or something. Let me see what my result was. Oh, 504, that's what it was. So I'm going to say this is 504 meters per second. So now I've got, just from using that type of expression in an old example that we did earlier, I now have the velocity, v bar, that I can put in there. I now have the n over v that I can put in there. So now all I got to do is say the number of collisions in the time of 1 millisecond is in fact number of collisions is equal to 2.69 times 10 to the 25th molecules per cubic meter. I'm going to multiply that by 4 pi r squared. And of course, r is 1.5 since the diameter is 3. So r is 1.5 times 10 to the negative 10th meters, and that has to be squared. And then I've got the square root of 2 in there. And then I've got 504 meters per second. And then I have times 1.0 times 10 to the negative third seconds. Notice the seconds hits the meters per second, gives a meter. And then the meter times a meter gives a meter squared. And then the meters cubed in the bottom gives just meters in the bottom. So basically, this is the number of collisions per meter, if you will, over a time of 1 1 millisecond. Let me double check my math there. Yeah, that was pretty good. Okay, so when I compute this, I'm going to get, and y'all should check me on this because there's a high probability I'll make some kind of mistake, 2.69 e to the 25th times 4 times pi. I'm using 3.14159 just because I'm obsessive, times 1.5 e to the negative 10. I don't trust just doing squared after that because I'm not sure if it's going to be a Wiseacre and just call that negative 10 to the square power. So I'm going to just write out 1.5 times 10 to the negative 10 again. And then I'm going to, that gives me that. Now I'm going to multiply that by the square root of 2. And now I'm going to multiply that by 504. Make sure I'm outside of the square root. And now I'm going to multiply that by 1 exponent negative 3. And from this, I get about 5.4 times 10 to the 6th collisions per millisecond. Okay, so we get literally millions of them, which isn't that bad. I mean, remember, we've got in a given cubic meter, we've got 10 to the 25th molecules in there. So it's not too bad to think that this only results in ultimately about 1 million collisions per millisecond. That would be in a given second, that would be basically 10 to the 9th per second. So we'd say 5.4 times 10 to the 9th collisions per second, because a millisecond, of course, is 1/1000th of a second. So I just multiply that by 1,000, and that's 10 to the 3rd. So that makes that 10 to the 6th become 10 to the 9. So that's part A. Part B, easy enough. I just use the formula, and the formula is Lm is equal to 1 over. Now, in this case, we're going to say 4 pi r squared square root 2 times just plain n over v, because remember the v delta t in the top and bottom canceled out. So I'm going to get 1 over 4 times pi times 1.5 times 10 to the negative 10 meters. That's going to be squared times the square root of 2 times 2.69 times 10 to the 25th, and that's molecules per cubic meter. So this becomes meters on top, which is what I expect. When I do that calculation, let me see, I get 1 divided by parenthesis 4 times 3.14159 times 1.5 e to the negative 10 times 1.5 e to the negative 10 times the square root of 2, 1.414 would be acceptable, times 2.69 e to the 25. And that should give me everything. And I get basically 9.3 times 10 to the negative 8th. So this thing basically makes it about 93 nanometers before colliding. And of course, it has about a billion, almost, since it's 5.4, it's very close to, in fact, 10 billion collisions per second. Any questions on that? If you read over that derivation, if you read over the derivation, your book does one like what I did when I derived sort of the ideal gas law by assuming that ideal gases are made of infinitely hard particles for which collisions are elastic. And when I did that collision, I was able to calculate the pressure And then pressure times volume gave me a very specific amount. And then I compared that, excuse me, to another result I had relating to temperature. And by doing that, I was able to find out a relationship between the kinetic energy and basically K times T. By doing that, if you follow those two derivations, you've got a pretty good understanding of how to do this sort of statistical analysis, or what we call kinetic theory, which is really just another version of statistical mechanics, which is a whole course you take if you majored in physics, and also if you did certain things within chemistry as well. So it's something super powerful. In fact, Einstein said if any of the major problems in physics are ever solved, he would put his money on them being solved by statistical mechanics, which really sucks because I hate statistical mechanics. Statistics is my least favorite mathematics course. And then thermodynamics is like my least favorite physics course. And statistical mechanics is often called statistical thermodynamics. And depending on how it's weighted, it often turns into one of those courses. So it's like the worst of the worst for me. But it is actually super powerful. So I have to at least admit that. So anyways, we will take it at that. Just know that it's kind of neat because when we use those things, we often find that we get the right results, even though we're using classical laws. So you can use the classical laws of statistical mechanics in a lot of cases, not all of them, as Planck showed, but in a lot of cases, you can use the regular Newton's laws and do statistics and come out with macroscopic answers about how microscopic things behave, even though you didn't use the correct framework, which is quantum mechanics. So, no questions on that? All right. Well, I'm going to go on then. This is kinetic theory of gases. We just finished solving a problem about the mean free path and the time between collisions. Now I'm skipping diffusion altogether, but I did want to talk to you about partial pressure and humidity. So there's this quantity called, let me turn it back on my face so I'm not talking to you while you look at a piece of paper, because then you'll pretend I look like a piece of paper, and that would be bad. All right. So there exists basically for all substances, when you go to dissolve something in something else, there's a maximum amount of the thing that you're dissolving that can go into the thing that's dissolving it. For instance, if you've ever made tea, so you make tea, especially sweet tea, you want to add sugar. Now, if you actually buy unsweet tea at a restaurant and it's already cooled down, and then they bring you out the unsweet tea and you add sugar, what you'll notice is very little of the sugar will actually disappear. Some of it will, but you'll still get this little residue of sugar down the bottom. And what's happened is for a given temperature, there's a certain amount of solute you can actually add to the solvent before it's fully, I want to say impregnated, but fully saturated with the chemical that you're trying to dissolve. And if you raise that temperature, that'll actually allow more of the stuff. And you might remember this from grade school. If you do that, so let's say you take something really hot and you dissolve a buttload of sugar in it. So let's say sweet tea. You dissolve a buttload of sweet tea or sugar in tea to make sweet tea. Now, if you slowly bring down the temperature very, very cold, you can actually bring it down to a cold iced tea type temperature. And it'll still have all that sugar in it, even though you're not supposed to be able to be allowed to hold that much sugar per unit tea at that temperature. It's called supersaturated at that point. And in fact, there was a very specific word, and it's neat that it is this word because that's exactly a word we use in a different context that happens to remind us that it's the same context. Does anybody know what happens or what it's called if I now take that supersaturated tea, the sweet tea, and add a single crystal of sugar to it? Something drastic occurs with the tea. Does anybody recall what that's called? Or does anybody recall what actually happens? I remember this from like fourth grade earth science or physical science or something, which it just fascinated me to think about it, but I sort of forgot about it for a long time. So what will happen is if you just add, say, one little crystal of sugar into that tea that's supersaturated, that will precipitate out all the tea that is beyond the saturation level that's allowed for that temperature. And that's exactly what's happening with clouds when they start to rain. So basically, clouds are made of basically water that's condensed out into, in some form, this cloud like structure of air. And once it reaches the saturation point, then all it takes is something minute like a crystal of water hitting it, or in the case of the tea, a crystal of sugar hitting the sweet tea, before all the excess supersaturated stuff precipitates out in what we call precipitation, i.e. rain, right? So that I just think that's kind of interesting and brings us full circle back to some of the science we learned when we were young kids and still interested in science in almost all cases, not just the nerdy cases, like me. So that's kind of neat. That being said, that means air can only hold a certain amount of water. And the saturation point is the amount of water that it can hold. And your book gives you some of those values, and it gives you what's called the saturated vapor pressure of water. So basically, once you add more and more water to the atmosphere, you could give the total amount of water in the atmosphere as grams of water per gram of air, or grams of water per cubic meter of air. But as you might suspect, since air is a gas, that could be a real problem because gases change wildly in terms of volume for a given sample for a given temperature. So what they do instead is they talk about the partial pressure of the diluted substance. So in this case, they'll say the saturated vapor pressure of water. And they have a nice little table in your textbook on page 484. And it says for a temperature of negative 50 degrees Celsius, which is freaking cold, right? It can actually hold 0.030 torr pressure of water. So in other words, if you're going to use the ideal gas law, right, and you happen to have been given the atmospheric pressure, what you have to realize is the air part of it, which is mostly nitrogen and oxygen, is not responsible for that whole number of torr. So they say, maybe they'll say, 31 torr or something like that. Well, lo and behold, 0.030 of that came from the actual water pressure. So you got to add that in. If they didn't give you the total pressure, you've got to add that in. Or if they gave you the total pressure and you're trying to use the ideal gas law to find out something about the air as opposed to the water, then you have to subtract that out. So that's something I hinted at before, and now you're seeing it. So in that table, yeah, it gives you the maximum saturation. So when we talk about the north being humid and hot and unpleasant, for instance, Georgia or Mississippi, or if you ever seen Biloxi Blues with Matthew Broderick, who I've met, by the way, kind of neatly at school. Anyways, he's one of my heroes for funniness between Ferris Bueller and various other movies he's been in. But anyways, he got to Biloxi, Mississippi, and he had signed up for the Army, and he said, "Is it always this hot here? I don't know if I'm going to be able to stay here if it's going to be all this hot." Which is funny because he just signed up for the Army, like they're just going to let you leave because it's hot. But anyways, the part of that rings funny is the fact that, yeah, we get a buttload of humidity, and when the humidity's high, your sweating don't help very much, because the only reason you can sweat is because you can add more water content to the atmosphere. But if it's already close to 100% saturated, i.e. the humidity's 100%, then that sweat that you just put out on your body is not going to evaporate and take away the heat from your body like it's supposed to, because that's the way sweating works. Sweating, actually leaking water out of your pores, does not cool you off. What does cool you off is leaking water out of your pores at 98.6 degrees Fahrenheit, say, and then having that water that's sitting on your skin now at 98.6, having that evaporate means that the warmth of your body added extra energy to that water to bring it up to the temperature it needs to actually evaporate, which is around 100 degrees Celsius. And therefore you lose some of that heat by giving it to that water molecule, or that sweat molecule, if you will, to cooling you down. So that's why the humidity is such an issue. Well, it turns out the humidity is very simply calculated. the relative humidity is the partial pressure of water that you experience divided by the saturation partial pressure of water vapor. So that's all you do to calculate relative humidity. Let me now give you an example to show you how that's done. So here is the problem we're working, number 2. It says, in fact, on a hot summer day, actually I just said a hot day, at 33.3 degrees Celsius. So this is number 2, and temperature is equal to 33.3 degrees Celsius. On that day, the partial pressure of water, so that's pH2O, is going to be 32.0 torr. And remember, torr is the same thing as millimeters of mercury. So on a hot 33.3 degrees Celsius day, the partial pressure of water vapor in the atmosphere is 32.00 torr. Part A, I would like to know what is the saturated vapor pressure at that temperature. So what is P saturation at 33.3 degrees Celsius? And then part B, I'd like to know, which I labeled C because, oh, no, I did actually call it B. What is the relative humidity? So I'd like to know the relative humidity, which I just told you how to do. So that's equal to question mark. And then part C is I would like you to know, at what temperature does water boil at the summit of Mount Everest? Okay, so that's part C. Let's say T boiling H2O at Mount Everest summit. So that's the other answer. So now I've written these down. I'm going to stop sharing the screen and let you see what I've written. Oh, actually, I'm just going to let you look at me. No, I'm going to switch it to the document cam. Hey, man, these are the jokes. Tell me how many other physics teachers you got that make funny jokes like this, or not funny jokes. Let's put it that way. So the first thing I want to know is what's the saturation pressure of water at 33, or excuse me, of our atmosphere at 33.3 degrees Celsius. So that means I'm going to refer to the table. So table, your book calls it table 18.2 on page 484. And this is of Giancoli. This is Giancoli's Physics for Scientists and Engineers. And it's actually the 4th edition, which they're getting ready finally to come out with a 5th edition. Okay, so according to that table, the partial pressure, the saturation pressure, excuse me, at 33 degrees Celsius is equal to, now here's the deal, the table gives me 30 degrees Celsius and it gives me 40 degrees Celsius, so I have to interpolate. So at 30 degrees Celsius, the torr value is in fact 31.8, and at 40 degrees Celsius, the torr is in fact 55.3. Okay, torr. So I want to go to 33.3, which happens to be, hopefully y'all notice that, is a third of the way from 30 to 40. So I need to go a third of the way from here to get the correct value. Well, if I ignore the fact that this is 0.3, that makes a problem. I'm going to call this 54.8 for a second. 54.8 minus 31.8 would give me just 13, or 1.3, excuse me. Now I've got to add to that enough to get from the 54.8 to 54.3. That's another 0.5. So I now have, instead of 13 or 1.3, I now have 1.3 plus 0.5. That'd be 1.8. If I want to go a third of the way of that, that's 0.6. So I'm going to add 0.6 to 31.8, and that'll give me 32.4. So this should be 32.4 torr. So that's the answer to part A. And that's just interpolating. And that's really what you're supposed to do with interpolating. If you're lucky enough to find that it's linear, where basically if I go up, in this case, I went up by a factor of 1/3 from here to here. If this also goes up by a factor of roughly 1/3, then you can assume the relationship is linear, and then you can just do a linear relationship. If I go up by 1/3 of this from here to here, then I only need to go up by 1/3 of this, and that works out fine. But sometimes you'll find that going up by 1/3 here actually goes up by, twice as much as 1/3, in which case you got to deal with other stuff. In this case, it's pretty close to linear. And in all cases, a linear approximation is a first order. You might find that it's not pleasant enough, in which case you're going to have to be a little bit more perfect to make it work. So anyways, we'll go with that. So there's our saturation pressure. Part B, they'd like to know, what is the relative humidity? Well, relative humidity is really the partial pressure of water that you have divided by the worst possible scenario you could have. The worst possible scenario you could have is 32.4 torr. And I mean by worst, I mean that's 100% humidity. That's when it's the most, really hot, oppressive temperature. And it also happens to be the pressure at which rain will probably occur. Okay. So I need to divide the actual pressure, which was 32.0 torr, by by the actual saturation amount, which is 32.4 torr. And I think you see that that is very close to 100%. And in fact, when I divide 32 divided by 32.4, I get 0.988, which is 98.8% humidity. So that's beastly. That's really miserable. But that's the way you work the problem. Relative humidity is just the partial pressure you have divided by the partial pressure at saturation. Now, part C is a little bit of a trick question, but it's a trick question in that I'm trying to teach you something that's very valuable to know when you're, taking a science course. In science courses, when you're reading your book, it's important that you literally look at every diagram, every figure, every picture, and read the things about it, because that you could not answer this question C unless you did such a thing. Does anybody know at what temperature water boils at the top of Mount Everest? Or does anybody know how I got that answer? Anyone? So water boils at 70 degrees Celsius at the summit of Mount Everest. That's the actual answer. Okay, the reason why, remember, water has actually air trapped inside of it. So it's got air dissolved in it, just like air has water dissolved in it, that sort of thing. When you actually heat it up, what you're doing is you're trying to get the molecules to move so fast that they can break apart from the other molecules that are next to it in the liquid. Because remember, the molecular model of gas is that the atoms or molecules are so far apart that they're not really feeling any force of attraction to each other, at least in the ideal gas situation. In a non-ideal gas, which is reality, there is a little bit of attraction no matter what. But in a liquid state, there's still a good bit of attraction, and they're sort of almost rolling across each other and stuff like that. So what you need to do is to make something boil is make the average translational kinetic energy of the molecules or atoms so fast that they can break that little bond that's happening and they can move freely. Well, when the pressure is so low, like at the top of Mount Everest, which is literally it's the elevation at which jets fly from one continent to the other. So it's a really, really high altitude, low pressure situation. At that low of pressure, there's actually less impetus to keep the molecules next to one another. They're more free to move around. And because of that, the boiling point drops considerably lower. That is, in fact, what was always used to figure out whether you had a high elevation or not. So if you walked along the Nile and continued along the Nile and you were trying to find its source, you'd keep checking at what temperature the water would boil at. And once you found the lowest temperature, then that would be the location at which you think the source of the Nile was, because that was the highest altitude around the Nile sources. Okay. So anyways, the way I got that answer was your book has a little dagger next to the 70-degree Celsius temperature on that table. And if you read the little dagger at the bottom, it says boiling point on summit of Mount Everest. Okay. So yes, even the footnotes and figures are often relevant. They're not always, and that's kind of sad because you sort of have to read them all the time just in case, even though in reality, they're not necessarily that important. So any questions on that? So despite that weird order that I went in, we are now officially completely done with chapter 18. I've showed you what I think is enough examples to figure out how to do stuff between that and, of course, the textbook examples, which, of course, you're always responsible for. Now I'm going to start into chapter 19, which is heat and the first law of thermodynamics. And in fact, next time, if I don't finish talking about it today, really all I'm going to get you to do out of chapter 20 is I want you to find as many versions of the second law of thermodynamics as you can. So I'm going to write this down so that you see it when you maybe download our Google Docs, but find as many versions of the second law of thermodynamics as you can. And commit them to memory. So it turns out there's, I'll give you a more definitive number when I go over chapter 20, but there's like one way of thinking about it is that heat never spontaneously flows from a cold object to a hot object. That's a version of the special or of the second law of thermodynamics. And basically, if you worked out, say, you take an ice cube and you throw it in a cup of water, and what you normally find out is that the ice cube will melt and the water will heat up. And in fact, if the ice cube has about the right mass, then the ice cube can melt and bring the temperature of the water from 20 degrees Celsius to say 20 or to say 15 degrees Celsius, right? Well, the first law of thermodynamics, which is really conservation of energy, would not forbid sort of this opposite thing happening. What would happen if instead you threw a 0 degree Celsius cube of ice, the same size as the previous one, into a cup of water? And before, what we said happened was the ice melted and the water got colder from 20 to 15 degrees Celsius. What if instead the water actually got hotter and went from 20 degrees Celsius to, in fact, 25 degrees Celsius, and the ice itself turned out to actually get colder and went from 0 degrees Celsius to, say, -7 degrees Celsius? I'm using numbers that are approximately right because I've done this calculation a bunch of times. And it turns out conservation of energy does not forbid that. The first law of thermodynamics does not forbid that. But we know it never happens. And the reason it never happens is the second law of thermodynamics. Okay. So that's the one version of the second law of thermodynamics. Another version is that you can never build a Carnot engine whose efficiency is 100%. You can never, here's another one. You can never build a Carnot engine or an engine or motor or whatever you want to call it. You can never build an engine that is more efficient than the Carnot engine. Okay. There's other ones for other types of engines. The total amount of entropy of the universe only goes up or stays the same. That's another version. So that's what I'm looking for, so y'all can have a better understanding of the second law of thermodynamics. And entropy, which has been called the measure of disorder, that's a fairly reasonable thing to think about it as, is the amount of disorder. Or another way of saying it is how many equivalent ways can you do something. So people have actually argued before, and I like this argument, that the reason why it's so much easier to get out of a parking space than to pull into a parking space is because of the second law of thermodynamics. So let me explain what I mean by that. So thermodynamics, the second law of thermodynamics really says that the entropy is the number of different ways you can have something. Okay. So the higher entropy state is the state in which you have many more ways that your end result is valid. And the way that has less number of ways that's valid is a lower entropy state. So when you go from out in the world, let's say a Walmart parking lot, into a particular parking space, you're taking all the different ways you can be sitting in that parking lot, and now you're forcing it to the very limited number of ways you can fit in the parking space. You can imagine, for instance, a parking space is like this. You could have your car against this side. You could have it a micrometer to the right, a micrometer to the right, a micrometer to the right, micrometer. You could have it all those different ways. And in fact, any number of small distances away until it gets to the other line, each of those is a valid way to park, right? You could also tilt it so that the front edge is just barely in the line and the back edge keeps moving further and further until the back edge is just lined up. And then you can do it the other way, and you do it. So you still have a lot of ways to fit in that parking space, but the number of ways of fitting in that parking space is way fewer than the number of ways of fitting in the world. Therefore, you went from a high entropy state that had a buttload of ways to be in the world to a low entropy state that had a very limited, although large number of ways to go into it. And therefore, it's harder for you to do that because you're working against nature. Now, when you go to pull out, you have your car parked, and there's only those few ways in which it could be parked, and you're going from a low entropy state to a high entropy state by pulling out. Therefore, you're going in the direction that the second law of thermodynamics would want you to go into. Therefore, you are doing something that's easy, and it's easy, therefore, to pull out of the parking space. So that's what I mean about chapter 20. I really want you to know those different ways regarding the Carnot engines and entropy and microstates and all that stuff. So start looking at that, reading chapter 20 and so on and so forth. Chapter 19 really is heat and the first law of thermodynamics. So I want to tell you something that happened and tell you something kind of neat about it in hopes that you can sort of understand this. So let's get cracking. So basically there was an experiment done by Joule. And Joule, I've mentioned to you folks before, was that dude that actually his family ran a beer company, and the beer was called Jowls. And so I don't know if you really should be pronouncing Joule as Jowls, but anyways, that was what the beer was called. And I think the beer still exists in Great Britain. At least I was told that 2 decades ago, so it might not be there anymore. But the big deal is this company, not only did they work on stuff like beer, but they worked on other things where it was very important to their livelihood to figure out how heat was transferred. So Joule did this experiment, and he wanted to see if mechanical energy was related to, let's say, thermal energy. So thermal energy being the thing that heats stuff up and cools things down. You know, when you take on heat, you warm it up, and when it gives off heat, it cools down. So is there any relationship? Well, his plan was pretty simple, but also kind of brilliant. You take a little spool, say, like so, and then you coil string around it, round, and then you run that string over a pulley, and then you attach the other end of that string to a mass M. Now you attach this spool, if you will, securely to a propeller blade. So it comes down into a liquid water. And that, of course, is a little propeller blade that actually spins water around and around and around. And he stuck a little thermometer in there, like so, and basically let this fall a distance h. And he said, okay, well, the mechanical energy given to the system was m times g times h, which would be measured in some number of joules. Okay. Then he measured the change in temperature. And in fact, that energy Q was the specific heat, or excuse me, the mass of the water times the specific heat of the water times the change in temperature. Okay, and this quantity would have come out in a number of calories. And I capitalized that just out of obsessiveness, not out of correctness. In fact, it should be a lowercase calorie. The uppercase calorie is, in fact, the dietetic calorie that we use, which is a kilocalorie. So just be careful with that. So when he did that, he found a unique relationship that we treat as a unit conversion, but it's not that. It's actually a fundamental conclusion, specifically that 4.186 joules of mechanical energy is equal to 1 calorie of thermal energy. So yeah, you've probably used this 1,000 times in chemistry classes and physical science classes and stuff like that to relate the calorie to the joule as this was a unit conversion. But in reality, it was a really big undertaking. There was no reason to suspect that, in fact, thermal energy and mechanical energy were at all related, but they are. Mechanical energy, which we measure in joules, is very much related to thermal energy, which we measure in calories. And you could also say, for instance, 4.186 kilojoules is equal to 1 kilocalorie, which is also equal to, and here's where I'm going to correctly use the capital, 1 capital CAL. Okay. So that was Joule's, one of Joule's major contributions. And we defined the calorie. 1 calorie is defined to be the amount of heat required to bring 1.000, in other words, any number of decimal places, 1 gram of water from, I think they said 31.5 or 32.5, or no, maybe it was this one. So calorie, yeah, 14.5 degrees Celsius to 15.5 degrees Celsius. Okay, that was how the calorie was defined. Maybe it was a little loose before, but now we've narrowed it down to a very specific 1 degree temperature change, 1 degree Celsius temperature change. It actually changes a little bit. So if I go from, say, 32.5 to 33.5 degrees Celsius, I'd get probably something a little different than a calorie. It's not exactly going to be a calorie, but it's going to be pretty darn close for any value of, actually I said 32. I was talking about Fahrenheit. But yeah, it basically 0.5 Celsius degrees to 1.5 Celsius degree would have slightly different than 1 calorie, just like 20 0.5 degrees Celsius to 21.5 degrees Celsius would have slightly different than 1 calorie, but we can probably, for most intents and purposes, use 1 calorie for any 1 degree Celsius temperature change. Okay, so that's the big synopsis. Now, with that, we have to use the idea that energy is neither created nor destroyed. So when we want to actually talk about energy, we either need to do something to make sure we're calculating all the energy, or we're accounting for all the energy that's trading hands or changing objects by either measuring everything that leaves our system and enters our system, or we need to make a system that doesn't lose energy. When we make a system that doesn't lose energy, or that we can account for all the energy, that study is called calorimetry. Okay, so with calorimetry, what you normally have is a container that doesn't lose much energy, and maybe you even have an extra way to see how much it does lose, so on and so forth. But that's a calorimetric experiment. So let's look at a particular problem. So it turns out if you actually make a plot of, let's say temperature versus heat added in calories. So if I make a graph, and we'll do this for water, but in principle, you can do it for anything. And I'm going to do it for degrees Celsius. And you plot this versus, let's say, kilocalories added. Your book does a graph of this, and that's good. That gives you the actual numbers. What I want you to see is the actual way things change. So what you see is starting at, in fact, this temperature might be, I think your book started at like -30 or -40 or some god awfully small number like this. Let's say -30 roughly. And that's not really necessarily accurate, but the main thing is I'm going to bring it up to basically the freezing point of water, or in this case, since we're going from a low temperature to a higher temperature, this is the melting point of water, which would be 0 degrees Celsius. So it turns out, in order to do that, to bring it, say, from some number of calories all the way up to the freezing point, that takes a certain number of calories, and we're going to say that's 20 kilocalories. Now here's what happens, and it's kind of neat. If you add any more energy, the temperature doesn't change until every individual molecule is now a separate part of the liquid. So basically all the little molecules stay together at a fixed temperature of 0 degrees Celsius until we actually put enough energy in there that it actually has every molecule or atom of the individual stuff, which in this case is water, as a liquid state. Well, it turns out that occurs once we've put in the additional 80 kilocalories. But that's a neat thing. That means that ice, once you get it up to 0 degrees Celsius, it fixes the temperature at 0 degrees Celsius until every drop of it, in fact, melts. That's the ideal scenario. For instance, if you really want a good Southern style sweet tea, iced tea, then what you really want is iced tea that's at 0 degrees Celsius. That doesn't mean, even though tea is, essentially water, that doesn't mean it's a solid chunk of ice. That means no, its temperature is 0 degrees Celsius, and it just hasn't gotten cold enough yet that all of it's frozen. Now, as you continue to add more and more heat, once it got enough energy to convert all of this solid into a liquid, then another thing's going to happen. And in this case, it's going to be a way more gradual slope, like so. Okay, in other words, it's not as steep as this one. We'll do that up until it reaches its next critical point, and that critical point will be when it goes from a liquid to a gas, and that's the boiling point. And that boiling point, of course, happens at 100 degrees Celsius. And when that happens, lo and behold, it actually stays a fixed temperature again. But the total number of calories for it to get to that point was like 200. Okay. Now it'll stay there, stay there, stay there, but now it's going to do something really crazy. It stays there until every molecule of the gas, or excuse me, of the liquid has been turned into a gas. And that turns out to be a whole above the 200, another 540 kilocalories. So, excuse me, it's now 740 total, but it's 540 beyond the 200. Once that occurs, then there's a very steep uh, curve for the water as a gas changing temperatures. In other words, the specific heat is quite high there. It's low here and it's medium here. So medium, low, and high is what I'm trying to get you out of this. And in each case, they're talking about specific heat. Specific heat is the thing that gives you an idea on average what the energy per degree Celsius change is. Okay. This is not true just for water. This is true about everything. But this is very important. This fact right here that it will maintain 100 degrees Celsius or 212 Fahrenheit for as long as it's boiling is the reason we use boiling in experiments as well as the reason we use boiling in cooking. If you take, say, a big turkey that has in fact been frozen and you don't want to get trichinosis or some other god awful disease from eating raw poultry, okay, then you need the raw poultry to be brought up to a critical temperature at which that particular bacterium or whatever would die, okay? So that means you need to bring the entire thing up to that temperature. Now, that temperature might be on the order of 160 degrees Fahrenheit, not 212 Fahrenheit. But by bringing water to a boil, you've now got a fixed temperature reservoir from which the turkey can still heat all day long. And of course, unless the water boils out, which you've got a whole nother problem, but you can continue keeping that in a bath of 212 degrees Fahrenheit if you can just figure out how long it takes meat and bone to warm up. Then you can hold it under that water long enough and it will eventually reach that critical 160 degrees Fahrenheit. That's what boiling's used for. Also, if you want to, for instance, figure out or get a metal to a very specific temperature so that you can drop it in a liquid and measure the change in temperature of the liquid and then use that to determine the specific heat of the metal, you need to know what the temperature of the metal is when you put it in. Well, the way you can do that is you can take the metal and submerge it in water and then bring that water to a boil. If you let that water boil long enough, since it's a metal, it's a conductor. It's going to reach this equilibrium temperature with the water pretty quickly. And you can tell, for instance, if the atmospheric pressure isn't freakishly high or freakishly low, then the metal, when you pull it out of the boiling water, should be 100 degrees Celsius. You can drop it in another vat of water. Once those two vats reach a common temperature, in other words, the water in the vat will increase, and then it'll level off, and then it'll start heating up the air, so it'll start to go back down. If you get that peak temperature at which the water in the vat reached, that would be the total temperature that this hot metal brought up the water. And you can use calorimetry to go back and calculate the specific heat of the water at that, or specific heat of the metal at that point. So that's really some of the usefulness of this fact that temperature remains the same when it's in the process of changing state. So this heat required to raise temperature is specific heat, and specific heat. But this is the specific heat of ice. This is the specific heat of water, and this is the specific heat of steam, which are entirely different. There's no reason for them to be the same. And in fact, the fact that these three slopes are different is me trying to tell you that they're supposed to be different. We know, for instance, water has a specific heat of about 1 calorie per gram per Celsius degree. Obviously, from this graph, assuming the graph is correct, that would mean the specific heat of steam is higher than 1 gram per Celsius degree, or excuse me, 1 calorie per gram Celsius degree. And we know that the water, in fact, would be considerably a little bit higher as well, but not as high as the steam one. Okay, so the ice would actually have a higher specific heat than 1 calorie per gram per Celsius degree, but not as high as the steam one. This quantity right here is really a heat of fusion. Okay. And this heat over here is a heat of vaporization.
And you said effusion, not diffusion, right?
Yes. Yeah, it's just plain fusion, FUSION. So this heat this extra heat you have to add to make it actually boil is called the heat of vaporization, because it's literally the heat required to add to turn the liquid into a vapor gas, right? The heat of fusion is actually enabled sort of backwardsly, because you're actually fusing the molecules of a liquid into a what I would call a fusion of a lattice of atoms and molecules. Okay, so that really is the additional heat that must be taken away to make the liquid go from a liquid to a solid. Okay, for instance, if you've we live here near Virginia Beach, and there's strawberry farms and stuff like that, and you'll hear that every now and then we'll have a frosty night even after spring starts, which is roughly 321. And when you do that, that can actually damage your strawberries. It can, in fact, damage all your various plants. If they're summer plants or annuals, they could be damaged by the frost. So what farmers will do is they'll spray water out on the strawberries uh, before a night of freezing temperatures. And what will happen is that water will actually freeze because the temperature is freezing, right? So when it freezes, it actually makes, because it actually makes a shell around it that is somewhat of a barrier. It's like a little coat that keeps the strawberries from changing their temperature very much. But also, in the process of it freezing, it had to release a little of heat that it had in it as a liquid state to become a solid state. That heat, some of which goes to the actual strawberry. So the strawberry gets a little boost of temperature from the water freezing, and it gets this little outer layer of ice that acts like an insulator that helps protect it from getting colder. So that's, another thing that comes in handy about the way matter behaves. So in an effort to show you that, crap, it's 7 o'clock already. Okay, let me quickly show you something then. I'm going to I'm going to share my screen, show you this last problem. I will let you guys, you might want to screenshot this so you can get it. But this is the problem. It's a stainless steel iced tea dispenser. It's filled with 4 liters of freshly brewed water, brewed tea. Need a word tea there. That's strong and sweet. Okay, meaning it's probably a little too strong and a little too sweet. It really needs to be watered down. So this is a process that actually works. So we'll say it just came off the boilers. It's 98.0 degrees Celsius, so it's just barely under boiling. It's only 4 liters. We're going to add 2 kilograms of a block of ice that's actually at -6 degrees Celsius. And we're going to lower it into the tea so we don't lose any. And we're going to assume basically that the stainless steel steals very little energy from the container, and the atmosphere steals very little energy from the container. So we basically can assume that every bit of heat that is leaving the hot tea is going into heating up the block of ice, then melting the block of ice, and then bringing the melted block of ice as a water state to a new temperature. Okay. So that's the calorimetry part. We're assuming all that's done. So I ask you how many joules, and also I want that in calories, will be required to bring the ice block to a temperature of 0 degrees Celsius. Then I ask you how many joules, also calories, will be required to melt the 2 kilogram block. So again, you're going to look up tables to find the specific heat of ice for part A. Then you're going to look up the heat of fusion for ice or for water for part B. And then part C, how many joules and calories would it take to bring the 4 liters of tea, which is now at 0 degrees Celsius, or which is now at 98 degrees Celsius, basically, up to 0 degrees Celsius, I should say down to 0 degrees Celsius. And what you'll find out is if this calorie amount is bigger than the sum of those two, then the tea will actually be brought down to 0 degrees Celsius before everything melts and comes to the same temperature. Otherwise, it won't be. So then I'm going to ask you to set all that equal now that you know what you know, and find out what the equilibrium temperature of the tea is when it's done. So I will let you guys do that example on your own. I guess I'll probably make a video of it and post it on YouTube. You have exceeded the time that you're required to be here, so of course you're free to go. Just remember, well, actually everybody got their test done. Just remember another test will be coming available. I've essentially covered the most important parts of chapters 1 through 19 now. I think next time I will cover a little bit of 20 and a little bit of what's left with chapter 19. And then by the end of next class, you will have your test available to you that will be due Monday by 5:45 p.m. So if anybody has any questions, please stick around. Otherwise, you're free to go.
Have a good night.
You too. Corey, do you have any questions?
I do, but it's kind of a long shot, but I just
Okay.
kind of had to ask just because I have to.
Did
But
you miss your test?
I didn't miss this one, but I did miss test 2 on accident.
Okay. That's not the one we did with the responders, so that shouldn't be a problem. I'll open it back up for you.
Thank you so much.
And let's say, since we got another test coming, let's make it due by Wednesday.
Thank you so much.
No problem. And I won't take any points off of it. I normally do, but I've been doing this at random for students that have asked, and I've also been doing it for students that didn't ask. So I figure it's probably fair to do it that way. Okay.
Thank you.
If you don't see it open up by tonight, send me an email to remind me, but I'm going to try to do it right after I get off of here.
Yes, sir. Okay.
See you, Corey.
Have a good night.
You too. Sean, are you still there, bud? Hey, Sean, are you still there? Maybe your speaker's not working. You can chat if you have a question. I can answer it that way. Otherwise, I'm assuming you're just not hanging out. So I'm going to split. I thought I heard you say bye anyways. Can we go back to 2A? Yes, gotcha. That's okay. So 2A was where I asked you the saturation pressure for temperature being 33.3 degrees Celsius. The textbook said that the saturation pressure at 30 degrees Celsius was 31.8. You got 39.6 torr. That might check. Let's check it out. So what I'm going to do to actually do this calculation, I will take 55.3 because I did do this in my head. So there's a high probability that you're right and I'm wrong. So I take 55.3 and I subtract from it 31.5. And that gives me 55.3 minus 31.5. No, that's not right. 31.8, sorry. Okay, and I hit a wrong button here. 31.8, and you get 23.5. Ooh, that was a problem. I see it already. I said 13. So it's yeah, that's definitely a problem. So I can see exactly what you got wrong. What you got is probably right. So now I'm going to take 1/3 of that. So 1/3 of 23.5. I said it was 13.5. That's a problem. And this gives me 7.8. So I'm going to add 7.8 to the small one. That should give me 39.6. And is that what I think that's what you said you got. So
yeah, that's what I got.
Thank you for catching that. Implies 31.8 plus 7.8 gives you 39.6. So these notes will show that for them. But yeah, thanks. Appreciate you catching that. Anything
Thank you.
else?
That's it. Thank you.
See, I'm horrible with arithmetic. Subtraction, I missed by 10. That's terrible. All right, have a good one, Sean.
Thank you, Professor. Have a good night.
You too. Bye-bye.